Hello everybody. In this video, I'm going to discuss one very important thing about the pumps, and this is something that relates to what we mentioned before in chapter 5 about the pumps and the equations that we use to describe the performance of pumps. Just to quickly remind or to have a quickly reminder about this, we have the term for H pump, and we put the U here to indicate that this is the usable pump head, meaning that this is the energy that the fluid already gained from the pump. And the reason we put this U to differentiate between the usable head and the electric or the usable work and the electric work that is consumed by the pump. And we said that not all the electric power is converted into mechanical work to the fluid because of the vibrations, the heat losses, and the noise. These are all energy losses, so this is why not all the electric energy is converted to mechanical energy. And this is why we have one term that represents the efficiency of the pump. And one other thing we mentioned here is that the Bernoulli equation that we see here is written in units of length. It's a meter or foot, and we can get the actual work or power gained by the fluid by multiplying this by mg. So this mg H pump is the work, the usable work by the pump. And this mass flow rate is the rho multiplied by the volumetric flow rate. And the electric power can be calculated using the efficiency, so we can use the same work or the power of the pump and divided by the overall efficiency to get the actual electric power of the pump. So there is one thing that we need to know about the pumps is that for a specific pump, for any specific pump, the power of the pump is always constant, meaning that it will consume the same amount of energy to run this pump. Okay, this is something that it's one of the specifications of the pump. When you buy a pump, you buy a pump that is 1 horsepower, quarter horsepower, half horsepower, whatever the power is, but this is the power of the pump. This is how you define the pump. It's not defined by the volumetric flow rate. It's not defined by the mass flow rate that it can accommodate. It's the main property that is used to define a specific pump is the electric power, how much electricity it consumes. And what I'm going to say is not valid for all the pumps, but it's valid for the most commonly used type of pump, which is called centrifugal pumps. And this is something I'm going to discuss after I finish the course. There are some extra videos that I'm going to do or include later because they're not part of this syllabus, so I'm going to keep them at the end. But anyways, for this pump, it can operate at different flow rates, meaning that the same pump can operate at high flow rate or at low flow rate. So we need to look at or take another look at the equation based on the information that we just knew here. We said that the pump head or mean the electric power of the pump is always constant. And for a specific fluid, the density is constant and G is always constant. And let's say for now the efficiency is going to be constant. So it's not 100% accurate, but let's consider that it's going to be constant. So we have two parameters now: the volumetric flow rate, which are variable, the volumetric flow rate, and the pump head. Okay. So if a pump is operating at and the rest of the parameters are constant. So if a pump is operating at variable volumetric flow rate, so the only parameter that will change to make this equation still valid, meaning that the right hand side is equal to the left hand side, everything else is constant except these two. So if the volumetric flow rate changes, the pump head will also change, so that the multiplication of these two is constant. So there's something we need to know, that if the volumetric flow rate increases, the pump head will decrease. And that's why for a specific pump, if we can operate the pump at variable volumetric flow rates, it means that the pump head will vary based on the volumetric flow rate. And because this is something that's very critical for the choice of pumps, if you buy any pump, you will find one of the information that you get with the pump. It's this relation. It's how much flow rate it or how much head it will produce for variable flow rates. And what we get for if we have it in a form of a graph like this, where pump head is on the left axis, and I mean the y-axis, and the volumetric flow rate is on x-axis, the relation will look like this, that it will decline as the volumetric flow rate increases, the pump head will decrease. So this is how this is the general shape of the pump curve, and this is a very characteristic thing to pumps. It's called the pump curve. So the pump curve is simply giving a relation between the head that the pump can produce for variable or for different volumetric flow rates. And this is called pump curve or pump performance curve. And this something, as I said, the manufacturers supply this relation as tables or as graph, where we have the pump head versus the volumetric flow rate. There is also one more piece of information that we can get, which is the efficiency of the pump. Okay. This is also one of the things that we can see on the pump curve. So this is an example of the pump curve. So you see here the this green line, solid line, is representing the pump curve, which is showing what we just mentioned, that as the volumetric flow rate increases, the pump head will decrease. And also it gives us another very important information, which is this red dashed line, which says the efficiency of the pump. Okay, and this efficiency, as you see, this is on the secondary y-axis. So we get the values of the efficiency here, not here. So you see the efficiency starts very low and it increases until it reaches a maximum value of almost 80 something. 81% almost, and then it declines again. Okay, so this is one more information we can get. So let's say the volumetric flow rate is 2 meter cube per second. So let's make it 3 meter cube per second. So from this we can know that the maximum head is going to be around 34 meters. And at the same time, at this specific volumetric flow rate, the efficiency is around 79%. So this is very useful because you can know if this pump is going to be suitable or not. So let's say for example, I have a process where I need a pump that will operate at this 3 meter cube per second, and I need a head of 30 meters. So this is 3 meters per second, and this is a head of 30 meters. So this is the point I'm interested in. So what I need is 30 meters per second, but what the pump can provide is 34, which is more than what I need, which is very good. So if I need 30, then the pump can provide 34. So this pump is suitable. It can provide more than what I need. While let's say we have another case where I have a pump that operates at 4 meters per second, meter cubes per second, and I need a head of 40 or 35 meters, for example. So this is 35 meters at 4 meter cube per second. This is what I need at this volumetric flow rate of 35 meter cube per second, but the pump can only provide 25. So the pump will not give provide the required energy to the fluid. So in this case, the pump is not going to be a suitable pump. So this is very useful because you can compare what you need with what the pump can provide. And based on this, you can easily tell if the pump is suitable or not. And also, from the same graph, you can use this efficiency to know exactly how much efficiency or how efficient the process would be in this volumetric fluid. And you might need to look for another pump that will provide or will operate at higher efficiency at this volumetric flow rate if the flow rate, the efficiency is not good enough. So this is simply the pump curve. There is one last line here, which is this dashed green line that we haven't discussed yet. And to understand this this line, this is called a system curve. So to understand what we mean by system curve, let's recheck the modified Bernoulli equation. We have here the velocities here and also here, and we can write this as the velocity as the volumetric flow rate over area. So if we write the volumetric flow rate over area, we'll have here v dot square over a squared, the same here and the same here, and we can rewrite the equation as you see here. So this equation is also giving a relation if we consider that the pressure is constant, the difference in height is constant, and if there is a turbine head that's constant. So of course the areas are constant, the rest of the parameters, if we consider all the parameters are constant, it's giving us a relation between the volumetric flow rate and the pump head. So it's similar to the previous equation, but this equation is giving us the needed pump head for different volumetric flow rates, while the other or the previous equation is giving us a relation between what the actual head the pump can provide for different volumetric flow rates. So both are pump heads, but one of them is the needed head and the other is the available head. Okay, the first equation that we discussed before was the available head that the pump can provide, while here is the head that I need for my process. Okay, so so now if we look at this equation, we'll see that as the volumetric flow rate increases, the pump head will increase, and this is very logical. You have a system and you don't have a specific pump yet, and you're just trying to find out your needs. So using this equation, you can tell for any specific volumetric flow rate how much head you need. And this is why in the same graph it was very useful that as you can see here, this is the system curve as the pump head increases, as the volumetric flow rate increases. And it's increasing in kind of a parabolic way because it's v power 2. So this is the what we call the system curve. So this dashed line represents my needs, and this green solid line represents what the pump can provide. So as long as I'm operating in this region where the actual head that the pump can provide is more than the needed head by the system, then the pump is fine. I can use the pump and I have no problems until we get this point of intersection, which is called the operating line here. This is where the needs are equal to the what the pump can provide. My needs are equal to what the pump can provide. So at this point, the two values are equal, and beyond this point, you'd see here that the needed head is higher than what the pump can provide. So I cannot operate the pump or use this pump at volumetric flow rates higher than this, but I can use this pump at lower volumetric flow rates. So this is the what we mean by a system curve, and the intersection, as I said, between the two curves is what we call the operating line. So this is a very important thing, and I hope I made it clear here. So inshallah, next time we will discuss one new topic in this chapter. So I'll see you then, inshallah. Goodbye.